Did you want to say anything by way of introduction while I'm getting this organized? Are you ready to go down there? All right, I need another second. So,
you need another second? Okay.
But we should be good. Pretty much.
So this is Professor John Sterman, and from the Sloan School of Management, and he's going to demonstrate the C-ROSE climate model.
Great, thank you very much. As Jennifer said, I'm John Sterman. I'm down at the Sloan School of Management. So while you've heard some phenomenal innovations coming out of the science side, what I'm going to talk to you about are some of the projects that we're doing on the policy side, in particular with climate science. So let me give you the summary in case we don't get past this first slide. I think you're all aware that the scientific case documenting that climate change is happening now, that the global average temperature is rising, that sea level is rising, et cetera, has never been stronger. The scientific understanding of these issues has never been stronger, and yet we have failed to reach any meaningful agreements at the international level or in the United States to reduce our emissions, and public belief in climate change is actually now falling, as recent surveys from Pew and Yale have shown. So we have a very important dilemma here. Science is not the bottleneck to progress on this issue. It's engaging the public and policymakers through the media in part so that the public understands the scientific basis for the urgency of emissions reductions and rational policy can be undertaken. In order for that to happen, it's not going to work to simply show people the scientific facts. That's known as the deficit theory of scientific illiteracy. It's just not true. If you just bombard people with the facts about what's happening, nothing happens. What's needed is for people to become systems thinkers, and many folks out there in the business world and the government world are talking about this. Here's a small quote from Jeff Immelt of GE, says, "I don't know all the answers, but what I do know is that leaders in the 21st century must be systems thinkers." And I'm going to explain what I mean by that, but the challenge is to make that real so it's not just a buzzword, not just a slogan. So how do you do that? Well, this is what I've been working on in my group, the System Dynamics group at MIT, for decades, mostly with business applications, but also with a range of environmental applications, including climate, as we'll hear today. And what we found is that you can't tell anybody anything. I tell my students on the first day of class, look, I can't teach you anything. Now, they've given me plenty of teaching awards, and they all kind of laugh, and I say, I'm dead serious. I can't teach you anything. All I can hope to do is to create an occasion through which you can learn important principles for yourself. How is that working in a complex dynamical system like the climate? Well, it can't be done unless people have access to what I'm going to call a management flight simulator, which is a model of how the climate works, but one in that they can interrogate and get real-time feedback, that they can ask any questions they want, that they can pose any policy scenario on the model, impose any policy scenario on the model, and see what happens, and change any of the assumptions so they can see what happens. So I'm going to show you that. The audiences here are basically everybody, but the way it'll work will be slightly different for different audiences. What we do with elementary school kids is different than what we do with CEOs, in a direction I'll let you ponder. I'll show you the model, I'll talk about how it's used, talk about next steps, and you should interrupt me as we go along if you have any questions. So, actually, it's that point in the afternoon where I'm sure you're not interested in a talk, so let's do a little experiment. So here's a website that contains a little experiment that I created with a student. He actually did all the hard work as usual. And the text, I know you can't read, but let me just tell you what it is. It's extracted from the Summary for Policymakers, the SPM of the IPCC's report. And our students have plenty of opportunity to read it as they do the experiment. It has some graphs showing historical emissions from 1900 through roughly today. That's emissions of carbon dioxide in gigatons per year. Shows the concentration of CO2 in the atmosphere, again from 1900 in parts per million. And it shows the temperature anomaly, so the rising temperatures. They have a chance to read this and digest it, and then they go on, and we ask them with instructions here that I'll just explain to you, what it would take, what kind of emissions reductions would it take to stabilize the concentration of carbon dioxide in the atmosphere at, in this case, 420 parts per million or so. Now, this is historic concentrations here, up from 1900 up through about 2000. And then if we want to stabilize at this kind of a level, the question that they're asked is, what has to happen to emissions? Well, down in this graph, we have over the same time period, so it lines up, the historic emissions of carbon dioxide in the red line, and an estimate, and it's an estimate, we're uncertain about the exact values, but an estimate in the green line of the net removal of carbon dioxide from the atmosphere. And so they can grab this and they can wiggle it around and change emissions. And now I'm going to ask you, what should we do? So, you know, I'm from the management school. We cold call our students. So if you would be so kind as to give me an estimate of what ought to happen here in order for emissions to drop enough off of business as usual so that this will happen down the road. And you can help him, all right? So, you know, one way to do it is, clearly BAU is not going to work, right? We have to drop emissions a little bit. So how much? You know, you can tell me when to stop here.
Below the line, it's already there.
10. Okay, let's go 10. Now that's an enormous change from business as usual. What you're calling for is worldwide emissions growth to be almost stopped right now. And just tiny little bit of growth going down the road. Well, let's see what happens. And by the way, a lot of folks who do this say exactly that. So let's see what happens. And it now shows you the result. If we did what you suggested, you would actually have a continuing growth of carbon dioxide in the atmosphere throughout the time horizon, out through 2100 and beyond. And the question is, why? Most people get this dramatically wrong. So why? Well, now we can wiggle this around and see what happens. And as I wiggle it, you see immediately what the concentration in the atmosphere would be. In order to get it to actually stabilize, I have to do that. Now, why is that?
Mass scale of population growth?
Nope. So that's an important issue, not in this model. I just have emissions and the removal.
Green line's removal, right?
Right. So the green line is the flux of CO2 that's being removed net from the atmosphere by natural processes. Where does it go? Well, it dissolves in the ocean and it's taken up by biomass. So what's going on here is actually very, very simple, but the vast majority of people who have done this experiment don't get it right. So how do you want to think about this? Well, come back to here. We've published the results of this experiment in Science at the end of '08. But let me just show you the results real quickly. 84% of the subjects of this experiment violated the principle of mass balance, the most basic physical law there is. And I don't care what political party you belong to, you can't moot that with politics. And 3/4 of them didn't even understand the equilibrium condition that you just articulated, that if you want to have stable concentrations in the atmosphere, you have to have the emissions no bigger and in fact exactly balanced by the removal flow. And 2/3 of them almost said that you could stabilize while your emissions continuously exceed your removal. This is a gross first-order error, and it biases people to think that climate change is less urgent than it actually is. Because if you believe that all you have to do is slow down the growth of emissions and you can solve the problem, you're making a huge error. We actually have to cut emissions significantly just to stabilize. Now, who were the subjects of this experiment? They were MIT graduate students. And the citations are here. There's several papers you can look at, the one in Science and the one in Climatic Change, that go into all the details. And that experiment's on the web, and you can try it. Go to my website. Question, go ahead.
You know, you can't give these experiments to the guys in the English department.
So you're being a little polite. What I usually hear is, well, what do you expect? They were business students. I just heard that at lunch today from a scientist. And what I got to tell you is our students at the Sloan School are extraordinarily well-trained in general and in science, technology, engineering, and math, STEM. 70% of them have their undergraduate or prior graduate training in a STEM field. Most of the rest of them are trained in economics or political science quantitatively, and only 3% of them were your humanities English majors. And when we've replicated this with other student populations and business and policymaker populations, the results are worse. So our students are great. I think they're fantastic. That's one of the reasons I teach here. But this is a serious problem. And it's not their fault. It's because the educational system, including they've had calculus, they've had linear algebra and differential equations. Many of them know a lot more of the science than you might expect. It doesn't help them think intuitively about these problems. So intuitively what's going on is you want to think about the climate the concentration of carbon dioxide and greenhouse gases in the atmosphere as just like a big bathtub. It fills up with emissions, and it's drained by that net removal flux. And this is a little piece that came out in the December '09 Nat Geo based on my work that shows this. And they did a terrific job with the graphic. And we all know how bathtubs work. You don't need to have ever taken calculus to understand that if you pour water into your bathtub faster than it drains out, the amount of water in the tub is going to rise. And yet, even though people have had the calculus and they've had the scientific training, they don't understand that intuitively. So there's a huge disconnect here. Also, people don't understand the complex feedback dynamics in the atmosphere. And I'll give you just one example. There are very many. But for example, methane and carbon dioxide, of course, are greenhouse gases. And as their concentration in the atmosphere increases, the average surface temperature will rise. As that happens, it stimulates bacterial respiration. Those bacteria are munching carbon in the soils, for example, which then releases more CO2 and more methane. If it's aerobic, you get more CO2. If it's anaerobic, you get more methane. And that leads to still more warming and still more bacterial activity that further accelerates the warming in a vicious cycle or a reinforcing feedback loop, exactly analogous to the reinforcing vicious cycles in the financial meltdown where people lost confidence in Lehman Brothers, and so they pulled their money out, which made them more insolvent, which caused people to fear bankruptcy and pull even more money out until the whole thing imploded amazingly fast. This is a picture of melting permafrost. There's 1.6 thousand billion tons of carbon that's been sequestered from the active carbon cycle in the permafrost of the world, and it's now beginning to melt out and becoming available for this process. And just to give you one little example, and I hope the sound will work here, we'll see. This is a little video clip of Professor Katie Walter up at the University of Alaska. She's standing on a lake, frozen lake, with her students, and methane has accumulated under the surface of the lake. And, well, watch what happens. We don't have the sound on. A brand new paper that just came out in Science has documented that, in fact, you probably saw this, there is now net methane outgassing in these regions under the Bering Sea, for example, that's increasing significantly. So now, people don't understand these complex dynamics. They need to understand them, and they're not going to be getting a PhD in climate science at MIT. So what do you do? Well, first of all, we have to recognize it's not just a problem of the subjects in my experiment or the general public, it's the policymakers too. So most of the negotiators in the Framework Convention process, and I was at the Copenhagen conference using our modeling tools, State Department uses them, for example. Most of the negotiators are not willing to go on the record, but one of them who is Christiana Figueres, who's the negotiator for Costa Rica, and she said, as you can read here, that the environmental consequences of the various positions and proposals are not clear to all of us, meaning the negotiators, and there's a dangerous void of understanding of these impacts. So the purpose of our model, which is called C-ROADS, Climate Rapid Overview and Decision Support, terrible name, but you got to have a pronounceable acronym, is to bring the best peer-reviewed solid science to the policymakers, the public, the media, and educators, civil society, in a way that they can learn it themselves instead of having those facts pushed at them, which we know doesn't work. So I don't have time to go into the details, but it's a physics-based model that has an actual carbon cycle and a radiative balance of the planet. We've carefully calibrated it against historical data. I really don't want to go into this except to say that this is a chart from AR4 you're probably all familiar with, and it shows temperature from 1900, up through 2000 data, and then various IPCC scenarios for what the temperature rise would be under different emissions paths that are named here. And there's a wide range of variation here. We've carefully calibrated our model to match the historical data, and it matches extremely well also on sea level. We also had a scientific review panel review the model. It was chaired by Bob Watson, the former head of the IPCC. You can see the names here. This is all on our website, climateinteractive.org. And they concluded that it matches the large-scale models extremely well and ought to be used as an official tool. Now, I could go into more detail, but instead, let's see if we can actually work with the model. So it's always a little bit of an experiment to do that live, but here it is. What you've got here now is a more sophisticated, carefully vetted, calibrated version of that little experiment that I just showed you, based on a real physics-based model. But it runs very fast, as you'll see. And you know, you might ask, well, why do we need a model like this when there's all these large-scale, serious GCMs and integrated climate assessment models? And the answer is they're black boxes, including to their developers, so policymakers aren't going to buy it. And their cycle time is so slow relative to the speed of negotiations. So when President Obama came to Copenhagen and negotiated the Copenhagen Accord, as it's called, that happened in 24 hours. You've got to be able to run these things through your models that fast if they're going to have an impact on negotiation. So what we've got here is a model in which you can see the US, the EU 27, China, India, all the other developed countries, and all the other developing countries on this panel. And there's more detail, so we can drill down and get the US, EU, Russia, Canada, Japan, Australia, South Korea, and all the other developed, and then separately also get China, India, Indonesia, Mexico, Brazil, South Africa, et cetera. So there's a lot of detail here, and you can specify emissions for each of those countries separately. In view of the time, let's go back and work with the 6-region version. So what I'm going to do first is let's implement the policy that the President has indicated the United States would be willing to commit to if everybody else would. And that is we're going to reduce our emissions by about 80% by 2050 compared to, 75% actually, compared to the 2005 value. Now you can change the base year you're using here. We can put in intermediate years so we can have different trajectories. I just want to do it quickly. And you see that as I move that slider, look at the blue line. That's emissions from the United States. It moves instantly. The model is simulating the entire global climate system that fast. And it's essential that the results are available that fast. If it takes more than about 10 seconds, you know, when you're briefing a senator, you've lost them. And you can see the impact immediately. So the little black line there is the business as usual concentration of CO2 in the atmosphere. And it gets up over 900 parts per million by 2100. That's just CO2. Other gases are in the model, but they're not on this chart. And the orange line there is the difference we've made. So now we've actually, just the US in this simulation, acting unilaterally. It does make a difference, but it certainly doesn't solve the problem. The blue line is the 350 target that's widely discussed. Well, let's add the EU. So they have a similar target. About 80% is what they discuss. That makes even more difference. Question? By when? By 2050, and then it stays constant after that. But you can change any of that. It's completely up to you as the user. I'm just doing a quick demo. Go ahead.
So is the idea here is that by putting someone in front of a computer and playing with these models, they'll kind of grok what's really going on rather than reading a paper on climate
That's not only the idea, but that's what actually happens. You can give them all the PowerPoint slides you want. It doesn't change their thinking, what we call their mental model. When they do this themselves, you can almost literally see the light bulb go on.
It's like they play God for a while.
Well, so they get to be in charge of policy and see what happens. And just in the as in the experiment that I showed for you, you put in these commitments, and you know, and then if you ask them, well, what's China going to do? Well, you know, their emissions are going to grow for some time, pretty much no matter what. They've got an intensity reduction target, but their GDP is growing so fast, their emissions are bound to grow. And so we can put that in graphically. This is just another way to get the input in there. So I can just draw what I think China's emissions pattern might look like. I can also get the data input from Excel, so I can really have carefully calibrated scenarios, and that's actually what our State Department clients are doing. But there's a scenario for China that has their emissions actually peaking and starting to fall by the end of the century, but not after another period of substantial growth. And you can see there it is right there, and it helps again. India isn't willing to do anything much at the moment. The other developed countries are pretty much willing to follow what the US and the EU are willing to do, so there's about 75% for them. And the other developing countries, their position, the G77, is basically we're not going to cut because we have to develop economically. So what's happened to total emissions? Well, there's BAU, total emissions, and now what we've done is we've actually stopped the growth at almost half the level that it was before, and a lot of people say that's going to be really hard to do, politically impossible, but at least it's going to solve the problem. And of course, it doesn't solve the problem because there it is. There's your emissions by region, and there's your CO2 concentration in the atmosphere. It keeps going up, not as much, but it keeps going up. Why? Because it's that bathtub dynamic. So here's the flow into the bathtub, total emissions under the scenario you just created. And there's the removal. Now, removal isn't just a line in this model. It's actually fully endogenous response to the carbon cycle concentrations, the forestation policy, deforestation policy that you can put in. I don't have time to do that, but you can put in RED policies and afforestation, et cetera. And this really does make a big difference in how people understand the problem. Here's temperature increase. So instead of about 4.6 degrees C expected warming with some range of uncertainty around that, now the expected warming is 3.6. So that's an improvement, but nowhere close to the 2-degree target that's widely discussed. And here's sea level. It's about 950 millimeters of sea level rise from year 2000 in the base case, and it's dropped only very slightly. By the way, if that happens by 2100, we're going to have to move the campus here, and we don't currently have a plan to do that. Now, one of the other things you can do here is we don't ask people to accept our parameterization. People have different opinions about, and there's legitimate uncertainty scientifically about some of the key parameters that govern the response of the climate to forcing by greenhouse gases. So one of the things you can do is, I've only got 3 of them here just for demo, but you can change any of those parameters anywhere in the model. So for example, our sea level module that you're seeing here, conservatively, everything in our model is based on the accepted peer-reviewed science. However, one thing we know is that there's a high likelihood that warming will lead to accelerating collapse of the Greenland and West Antarctic ice sheets, but whether and how fast that happens is very poorly constrained by the data. So we've left it out to be not overstepping the peer-reviewed science base. But you need to have the ability to see what would happen. So I can just pull this slider here and add, I'll just add half of a millimeter per year per degree of warming of additional sea level rise from ice sheet disintegration. And now you can see that even with our emissions reduction, sea level rise would be well over a meter. And if the climate sensitivity is higher than 3 degrees, which is the best estimate, but there's a big band of uncertainty about that, and 4.5 degrees is well within the envelope of the probability distribution, now sea level rise is approaching 1.5 meters, even with the policies we put in. Now you could say, well, maybe things are going to be better and climate sensitivity is going to be only 2 degrees or 2.5, and then things would get better. But it's up to you. Now we can, I won't show it to you for time, but we can run this model using a full-bore classic, multivariate Monte Carlo sensitivity analysis, so we can generate all the multidimensional probability density plots showing the uncertainty bands. I got to tell you, the people in the policy world, much less the general public, just doesn't understand that. They think a PDF is one of those documents that you can open on any computer. So we found that having this ability where they're in charge, they put in any number they want, they see the immediate feedback, really helps them understand what's going on much better. And there's other data here, how much CO2 per capita in each region, how much CO2 per dollar of real GDP in each region, et cetera, et cetera. But let me try to wrap it up here by telling you how this model is being used and what our next steps are. So it's being used by a variety of groups. In the policy and negotiating community, the State Department uses our model, and we can say so publicly. So Todd Stern, who's the senior climate negotiator for the U.S., his deputy Jonathan Pershing, they use this model. There's a more sophisticated version that I'm not showing you today that they use, and we support them in doing that. But they have the internal capability to do that themselves so that they can run their own confidential scenarios. We're working with China now, and other nations are interested. We're also reaching out to the public. You can't address this problem just with the policymakers. Even if a perfect agreement had come out of Copenhagen, it would be DOA in the Congress and in Delhi and in Beijing and every other capital around the world, because there just isn't enough public support for the legislation that's needed. So you got to get the public engaged, and we do that in a variety of ways. There's a State of the Global Deal widget on our website. So if you go here, which is the Climate Interactive website, climateinteractive.org, and you click on this, it's a, should be here. There, it's a little down below. We have a little widget here that shows the state of the global deal. Now this is a widget, so you can embed this on your website, your blog, your Facebook page, and every time we update it, because in our judgment proposals have changed, it'll automatically update on your Facebook page. And what it shows is here's the 1.5 to 2 degree target people talk about. Here's the 4.8 degrees centigrade, and if you're American, get it in Fahrenheit. So the 8.6 degree F rise under BAU, and the current, what we call plausible commitments that nations have made. These are the things that they have now, as of January 31st, put their name against on that originally blank appendix from the Copenhagen Agreement. It gets us down from 8.6 to 7 Fahrenheit, down to 3.9. So it's better, with, with an uncertainty band that you can see there. It's better, but it's nowhere near where we need to go. The crawl here is the list of the confirmed proposals, and you can drill down and get all the detail, all the documentation back to the primary sources so you can see exactly what we're assuming about which nations are proposing what. Every time a nation changes their proposal in either direction, we update this analysis and it updates automatically in your Facebook page. I don't have the current stats, but there have been many, many, many thousands of embeds of this in various web pages and so forth around the world. The third thing we're doing is to reach out to the public. We have a free online version of the model that I just showed you that runs over the web for free called C-Learn, available at that same website, and a role-playing negotiation simulation of the framework process. So you can simulate what the negotiators are doing, which I've developed with my colleagues, and that's available also for free. And on our website, you'll also find full technical documentation of the model, a facilitator guide for that, videos of us leading it, and we know that that is starting to be used. People are able to go to the site, look at those materials, and then run it themselves on their own in their classroom, down to middle school, in college, and in corporate boardrooms, and we know that that's happening. So let me stop there and see if there's any other questions, and you can get further information from me or at climateinteractive.org. Yeah?
I was just wondering how some of the recent uproar is affecting what you're trying to do over people saying, oh, there's, some climate scientists are hedging their results, and there was something in the New York Times yesterday on the cover about how they're trying to get, evolution and climate change.
Yeah, that was an extremely depressing article. So no question that ClimateGate has hurt the public's belief in and understanding, but in fact the careful audits of that material shows that there was no fraud, and in any case it doesn't alter the scientific foundation for the paleo record or for the urgency of the issue. That's not understood. I guess my feeling about this is it's another demonstration of, I'm just going to say it as bluntly as I can, the utter bankruptcy of the theory that if we just tell people what the science shows, they'll believe it, and then policy will be carried out on a rational basis. That's just wrong. A colleague of mine, Randy Olson, the filmmaker, some of you may know him, his metaphor about this, he says the scientists versus the climate deniers, it's the Cub Scouts versus the mafia. And we've just got to get a lot more serious, but without overstepping the science ever. So maybe it won't work, but our approach here is everything in here is absolutely solidly grounded in the peer-reviewed science, and you don't have to take our word for it. You can easily dig in and determine that for yourself, and you can try your own beliefs. But by making it interactive, people can perhaps come to some understanding of what's going on that will help them move in the direction of supporting policies consistent with with the science.
Thank you.
Great, thank you very much.
We still have two more presentations, and if anybody's sort of worried about if people are going over to the showcase tonight, there's shuttle buses from the Kendall station every 10 minutes going over there. So starting at 4:40. So don't worry too much about that. Do you have your slides?
Oh, Dan's talk. Yep. I gave that down in DC.
Yes, I ran through, it's good.
Come on now. Good afternoon, folks. My name is Louis Ortiz. I work as the research director for Professor Sadoway here at MIT, and I have a great opportunity to talk about a new technology, a new battery technology called the liquid metal battery. It's aimed at grid-scale storage applications. These are largely stationary applications, and so when you start to think about stationary applications, you have to think about what the requirements are for those applications. Key thing being, you don't want to pay for anything that you don't need. In a stationary application, you don't end up in the same type of product liability for mass market consumer goods such as cell phones and automobiles. So you might be able to relax some of these, well, I mean, safety is still important for this application, but not as important as that situation. So we might be able to relax certain requirements such as an ambient operating temperature. Maybe we can go to high temperature now. But the important thing is when you relax those options, it gives you an opportunity to have a new design space, a new way of thinking about energy storage, a new way to get into an application space that's highly cost intolerant. And that's the whole thing, is if you have an innovation in batteries for stationary storage, it better be cheap. And how cheap? Well, if you look at your laptop battery, your cell phone, you buy a replacement battery, you're paying thousands of dollars a kilowatt hour. If you go into automotive, the application requirement is in the range of $150 to $200 a kilowatt hour, quite significantly below that. Now you go into stationary, renewable deployment, those type of things, you're down at $50 a kilowatt hour, pretty far away from where typical batteries are located. Now, why is it that those costs are so low and that the limits are down there? Is because you're not competing with batteries anymore. You're competing with the natural gas peaking unit. A big can with a nozzle on the end that you can stick natural gas into and get electricity out the other side. That's the option when people want to deploy renewables or do things on the grid. That's the option you're comparing with, and that's the price point, a very low price point. So in this setup, what you have is the severity of the operating conditions increases as you go down, but the price tolerance increases as you go up. This is a tough nut to crack, but you know we're taking a shot at it because it's an important nut to crack, both for renewable deployment types of things, getting power from the wind when the wind's not blowing, power from the sun when the sun's not shining, trying to help out with stability in the grid. Those are important applications as we try to change our grid or to try to improve the amount of renewables. So that's why we're trying to go after this one. One of the examples of motivations, let's think about some of the power outages. Some folks may have been around back in 2003 up here in the Northeast and got caught in the blackout. What was that blackout? It was a tree that fell in Ohio, knocked down some lines, and cascade effect, we have a blackout for many different states, as much as a week in certain places. This is due to the fact that the grid is unbuffered, it's stressed, it's a complex system, and it's very easy for things like these to happen, not necessarily in the same scale, but if you look at it, you know, we think about the storage that we have. In the United States, we only have 2.5% storage capacity compared to the EU and Japan. That means that's the proof about us having an unbuffered system. We don't have a lot of ability to take freak events and keep them cascading out of effect. If there was storage near where that tree had gone down, and the operator, the grid operator, could have diverted some of the, I forget in that one, I think it may have been a frequency or voltage regulator. I'm not sure exactly which one. But if you have storage, you get opportunities to manage the grid much more efficiently. And you don't have to have as robust a grid. So, and then the other side of it is sometimes there are people that actually want to actively promote these type of things. Storage can help you with that as well. Additionally, let's look at the cost of this. If you have no storage in your system, just the cost of the blackout, quite expensive. And if you look at even the small power outages versus small duration, like under 15 minutes down to 5 minutes, all the way around, that's like $119 billion of outage costs. That's almost half of the total cost of electricity. Outages are a severe issue. So yes, renewable deployment has a lot of value and a lot of need for storage, but even just the surety of our grid, national security, those type of things, they need storage as well. Thinking about the grid a little bit more specifically, I kind of call this the last 5%. For the demand of 400 hours a year, the grid has to be oversized both in the amount of distribution by about 25% and 10% of generation, because of the fact that there's peak in demand. And they have to oversize this. They have to spend a lot of expense for this small segment in time, this last 5%. And that's a key problem as the growth is going up and an area where storage can have an application and opportunity. So now if you want to put a battery into this situation, these high power situations, what you run into, and any fuel cell person will tell you, this is the battery conundrum, right? You typically cannot get both high energy and high power in a battery. Why? Because in the high energy situation, what you want to do is you want to have very thick electrodes to get really good packing density. You get great energy in this setup, but unfortunately you don't get good power because you can't pull out a lot of current out of that situation. Because typically these electrodes are not highly conductive, or you add in conductive additives. So if you want to get power, what you do is you thin it up, you roll it up like a jelly roll. This is the way most of your lithium-ion batteries look. And unfortunately, then you sacrifice some of your energy. You end up in this conundrum of energy and power. You got to pick your application. And for this application, it actually needs a lot of both, depending on where you're going to stick it. So there's only so far, and additionally, there's only so far you can go delinking these aspects. So that's where the invention opportunity came for the liquid metal battery. Professor Sadoway, graduate student, the typical professor and a graduate student, Professor Sadoway and David Bradwell, kind of looked at this issue, looked at the challenge, and decided that they want to try to think differently about the solution. So what did they do? How did they get into this? They decided to think differently. Instead of trying to teach batteries that don't like these high powers how to get bigger and how to take higher power, why don't we go the opposite direction? Why don't we find the biggest current sink and see if we can teach it to be a battery? That's the change in thought. And myself, I also have a metals industry background. I did my PhD with Professor Sadoway. So coming from the metals industry, we knew a big current sink. It's an aluminum smelter. That's why they're sited next to all these hydroelectric. This pot line has 200 of these pots. They're 40 feet long by 10 foot wide. They're running 500,000 amps at 4 volts. And what if we can turn this into a heavy-duty battery? What does that look like? It's multiple megawatts going through each one of these cells to make tonnage aluminum at less than 50 cents a pound. That's something that has the opportunity to hit these type of cost products. But, I mean, maybe the aluminum industry already has this problem solved. Is the aluminum cell a battery? It could be a battery, actually. If you look at it, what you do is you operate at 900 degrees C, and your ore, your feedstock, where you're going to get your aluminum from is aluminum oxide. In order to dissolve that in something, you need to use a molten salt. So you're up at this high temperature molten salt, the alumina dissolves in here and you pass current. And what happens is you deposit liquid aluminum on the bottom, and at the top electrode you end up with a reaction making oxygen. You make oxygen, it reacts with carbon, you have CO2, and it bubbles away. So our ability to turn this back around, to get that energy back, not going to work because you just lost your product. But, you know, the next thought is, well, maybe what we can do is we can just put a lid on the top so that it doesn't bubble away. Unfortunately, the gas is not a very good conductor, so it doesn't make a very good electrode. So taking an aluminum smelter as is and making it a battery, not a good solution. But that's a great answer for an inventor. That's an opportunity to innovate. So what was the innovation? The idea was, let's replace this top electrode with a liquid metal so that we can reverse the reaction. So we produce metals at both electrodes, or ambipolar electrolysis, and that was the genesis of the liquid metal battery. Now, what does this do for us? Well, I was showing you the two different options, this energy versus power. In this situation, we can size the battery to have as thick electrodes as we want because they're metal. They have high conductivity. We can get power through them. We can size them for energy and still get good power. And then how does this actually work as a battery? Well, on charge, what we're going to do is we're going to make magnesium at the top electrode and antimony at the bottom electrode. Now, if we want that back, well, magnesium and antimony would love to react with one another. Unfortunately, this electrolyte's in the way, separating, keeping them from reacting. So in order for them to react with one another, what they have to do is they have to dissolve. And actually, I guess this did get munged a little bit. Let's take this arrow and have it go the other way, this arrow that way. So what you're doing is you're taking the two liquid metals, they dissolve into the electrolyte, and force current through the external circuit, and you can have a load. That's how you've reversed your metal production into a battery. And so what does this give you? It gives you something with very high charge capability, something that will give you high currents at a good efficiency. Also, it's a very robust system. These are liquid-liquid interfaces, so they're high connectivity, but they're also very robust, literally floating upon one another. So you get good cycle life. You have an opportunity for something that can last for a long time. You haven't heard about aluminum smelters closing down just every other day. That's because they're very long life. This is leveraging that kind of an approach. And as I was saying, kind of going the same way, this looks more like a primary metals industry play than a battery industry. Because what happens is Alcoa, when they want to make this pot line, they don't just go out and build it themselves. They go to SNC-Lavalin, who works with Bechtel, to come up with a system for making this at a price where at a cost where they can sell aluminum at 50 cents a pound. That's an ecosystem that we can plug into, and that becomes something that will allow us not to worry as much upon scale up about what the derating is on a battery. And I'll show you in just a second where that fits in. It's right here. So what are the economics of this application? Once again, we need to be below $100 a kilowatt hour. We're shooting for 50. And if you compare it to the other technologies out there, and everybody puts up this graph, and theirs is always the best one. But what I've done here is I've taken the cost of energy storage along this axis, on a log axis, and the cost of power. And then this upper right-hand corner is the low-cost situation, the critical area for these stationary applications. And so if we just look at our active materials costs, we're in a great position. And then if we derate that to go to an actual system, we end up in an area where the rest of the technologies really don't play. And the justification, we took actually a pretty conservative justification as to how much, meaning we said it's going to cost a lot, a big derating to get to this point. But we don't think it's going to be that bad because, once again, we get to stand on the shoulders of 150 years of primary aluminum manufacturing and technology development. So how do we get these actual estimates? Without going through the nuts and bolts, unless somebody wants me to stop, we've looked at a number of different battery couples, and we looked at both the volumetric energy density as well as the specific energy density. And what you tend to find is, even compared theoretical to theoretical, we've got their energy densities that are pretty comparable to existing battery technologies, and in a lot of cases better. But that doesn't, at the end of the day, that doesn't matter. Everybody that comes in and wants to talk about a battery technology wants to know about energy density. But it's cost. Cost is the real king here. And here on an inverted scale where a big bar is low cost, that's where this technology really shines, and that's the critical metric. Even so, we still think it looks as though these technologies are going to be better than lithium ion, yet cheaper than lead acid. That's an opportunity in stationary storage to have a real impact. What have we been doing? You see right here a cell that's been cross-sectioned after operation at 700 degrees C for a couple days. At temperature, we get 3 liquid layers. Obviously, at room temperature, now they're solidified. And you can see from this centimeter scale that we're still pretty small. But we're able to cycle this, and we're able to get energy back out, most all the energy coming out. But we have a lot of challenges still. We still need to see the scaling laws. We need to see if we can improve the cycle life and what kind of failure modes are happening. Still a lot to do, but we do have, the concept does have the ability to store charge efficiently and return it. And the costs seem to be in the right place. The materials that you can use end up costing out where the application desires. Let's see what the next thing. So let me talk a little bit about our sponsors and what kind of projects we're working on right now. Everything got started through grants from the Dispatchable Center. They were a great initiator for a very fragile idea to try to get some of these first cycling information. The Energy Initiative, through its sponsor Total, is looking at some home storage opportunities. ARPA-E has a grant for us trying to look at, say, neighborhood level type applications, helping us scale once again. And helping with this ARPA-E project is some cost share, both from Total, but also the Chisonas Family Foundation, Lightspeed Venture Partners, the Clean Energy Center. These are all the people that are kind of helping us with our cost share for this, because that's actually rather difficult in a university to get cost share on a $7 million grant to get us up to $9 million. And then DARPA has some not only are they worried about some of these surety issues, these outages as they relate to their military bases, but they also have some other applications. We have a seedling from them and possibly a program coming on soon after that. I'll end with just a picture of the team, people that are working both on this and some other storage stuff, and just thank you for your time. Yes, sir.
Sorry, this is a stupid question, but what's the connection between your proposed process and the aluminum smelting industry? I mean, is it just like you would use similar industrial processes to make these?
You could make the same, you could use the exact, imagine this, let's see if I can get there. Imagine this line, this pot line right here, as a battery. That's the idea. Each one of these cells, string them together as a battery, and this could be multiple megawatt hour size battery. Because what we do is we still use this basic approach where you have a liquid metal down here, and now with this electrode, we've got a different liquid metal on top, and we've got the protection of the frozen sidewall, so we get long cycle life. But imagine this. We don't know how small we can get it, at which we can get these scales, but imagine this unit as something that might stabilize a wind farm. Yes, sir.
Could this be, I mean, I'm probably, there's no chance of incorporating this as an industrial manufacturing process so that most of the time you're refining material, but you're also acting as a storage unit?
It's a possibility. One of the things that's unique, this concept of making metals at both electrodes, is that in the same cell you could actually make two different metals, and that's kind of the scientific curiosity side. I guess there is a possibility. We're not really looking at aluminum as the one. So the problem is that everything that's going to come off at the other electrode, they typically don't deposit in the same ore. So it's kind of hard to do it both ways, but in concept, it's the same physical type of setup, yes.
How much thermal loss is there, you know?
Right now, well, everything that we've estimated, both on these as well as other high temperature battery systems, they're able to, you use the thermal losses to keep this side level, and it's so you end up in an energy efficiency range total of about 80%. So about 20% of your losses have to do with the thermal losses. And
if you're on standby, how much energy does it take of the battery's overall capacity to keep this thing alive?
It depends on what your use profile is. It depends on how you want to, whether it's not really, if you're looking to go on standby for a long time, like a UPS type application, this is at least right now not well set up for that. But on the term of hours, the thermal mass of these things are such that you don't have to bleed current through it to keep it warm. The thermal mass is enough that maybe you freeze a little bit off the sides. You know, you start to freeze, but as soon as you start it back up, it's going to remelt and that kind of stuff. Just on the order of hours, if that's the order of your standby. But if your order is days, then you're going to start wanting to try to bleed. And we've estimated, based on the calculation we've done, that it could keep itself alive on the order of a month or more. Yes, sir.
And much interest from energy companies or utilities?
Total, a French energy company, they're looking at it for home. Lots of people have a lot of interest. It took a little while before somebody was willing to kind of take the jump into the basic research that's going. Lots of interest, but they want to see something at scale before they want to jump in. Thank you.
Thanks very much. We have Michael Greenstone from the Economics Department next.
try this one more time. Sorry. There we go. How do I do this with a new PowerPoint?
Oh, it's left here. Beginning or actually, I think it's going this way.
Okay, so sorry about the old title there at the bottom. Thanks very much for having me and taking the time. I know it's been a long day, a lot of ideas flying by. In the last few minutes, cut 5 slides, so hopefully you'll thank me for that at the end. Okay, so what I'm going to try and talk about is, so the title is Unequal Burdens Predicting the Mortality Impacts of Climate Change in the U.S. and India. And what I'm going to try and talk about, try and answer 3 specific questions. And this is based on a series of papers I've been writing. The first is, what is the impact of interannual variation in weather on health in the United States and India? And the second question is, why are the mortality, or should I guess be trained, the answer to the first one, why are the mortality consequences dramatically worse in India? And the short answer will be adaptation, and I'll come back to that in a second. And then I guess this one, there's a snafu here in my typing, but what are the implications for kind of coming to an international agreement a la Copenhagen on climate policy? So this graph is, or something like it, is pretty familiar, I'm sure, to most people in the room. It's a graph of temperatures from 1000 through the present. It has a kind of famous Al Gore hockey stick to it. So temperatures have definitely started to increase. One thing that I think has not been as well appreciated, so this is mean global temperature, is, and here we're going to just taking kind of a standard climate model and business as usual scenario, we can take it out to 2100, kind of extending that graph from where it was. And so you can see there's projected increase. This is a global mean temperature of about 7 degrees up to about 49 degrees Fahrenheit. So one thing that has not been, I think, especially transparent is there's a lot of, when I began working on this, I thought, oh, well, the whole distribution of daily temperatures is just going to move a little bit. And it turns out when you unpack the predictions, and all these models give you daily predictions, and so they have daily temperature predictions for every single day, through the end of the century. And what you can do is look at those instead of just looking at the global mean. And what's really striking about that is it's apparent here. So the lighter color here is the distribution of annual daily mean temperatures in the United States currently. And it's just binned up into 10 different categories. Less than 10 degrees Fahrenheit, 10 to 20, 20 to 30, all the way up to greater than 90. And let me be precise, annual daily mean, it's the average of the high and the low. So a day greater than 90 is pretty hot. You'd have, if your low was 80, you'd obviously have to have a high of at least 100 to get in there. Now, as it's currently, current temperatures in the United States, the average person in the United States faces just about 1 day a year where the average daily temperature is greater than 90, and that's because most people don't live in Arizona. In Arizona, it's obviously higher, and this would change as you change the geographic distribution of people. But as a thought experiment, let's just hold the geographic distribution of people constant. Take the climate change models for what they predict for 2070 to 2099, and how would the distribution of daily temperatures change? And that's what the red bars are trying to tell you. And the truly astounding thing, at least in my eye here, is we would go from the average person facing 1 day a year where temperatures are greater than 90 to about 30 days a year. And in the 80 to 90 range, we'd have an increase of about 50 days a year. So it's not just that average temperatures would go up by 7 degrees. You'd get all this piling on at the high end of the distribution of daily temperatures. Now, it's kind of fun to look at that graph, and it's a different way to display data. I love displaying data. But I think what's really important about that is that we think all the bad stuff associated with climate change is going to occur at the tails of temperature. So going from 65 to 70 doesn't really change much. But all the mortality and the agricultural impacts and things like that, they all happen, the bad stuff happens at the really hot days. It also happens at the really cold days too. But as you can see, we're not going to lose that many cold days in the process. So that's the starting point. And I can make a similar graph for India, which I've done. So what I did is, what I did was, so I have this as background. And then what I did was try and find out, well, what's the relationship between mortality and daily temperature realizations in the United States and in India? And people have previously done that by looking at these kind of daily studies or looking at heat waves. And they say, well, you know, there's a heat wave and plenty more people die on the day of the heat wave or a couple days after. And then the problem with those kind of studies is a lot of people in epidemiology, giving economics bad reputation, it's better that this didn't come from economics, but they call it harvesting, which is you have a lot of people really, really sick, and then some discrete thing happens, like a heat wave, and it causes them to die just a few days earlier. And so there's not much loss of life expectancy. So what I did was try and relate the annual mortality rate, which should not count any deaths that were just sped up by a few days, against the distribution of days in each of these temperature bins, both for India and the United States. Okay, and the results are here. So why don't we just focus on the red line, which is India. And what that's trying to tell you is on the y-axis is there's log annual mortality rate. And what that says is if you take if you take a day from the 50 to 60 range and move it to the greater than 90 range, the annual mortality rate in India will go up by 0.7 of a percentage point. There's an incredible increase in the annual mortality rate. And remember, as the previous graph showed, you're just going to get tons more of those days. The India graph would show you the exact same thing. And what is also true in India is that there's kind of this U shape. Cold days are really bad too. So what climate change is, so that's the India response function. The U.S. response function, which is, and I should emphasize, these data are based on millions and millions of observations. In the United States, it's every single death from 1968 to 2002. And in India, it's from 1957 to 2005. The truly amazing thing, in my view, about the comparison here is that in the U.S. there's basically no relationship. I mean, if you stare at it hard enough and you were to change the axes, you'd see a little bit of a kind of flattened U relationship. But basically, temperature doesn't kill us in the United States anymore. And the reason is because we're rich. And what does being wealthy allow you to do? It allows you to protect yourselves from heat and cold, for that matter. And so that's kind of the thesis of this talk is this underscores, you could think of this as showing two things. If India were suddenly at the end of the century, the current India, the mortality impacts would be devastating. And in the United States, they wouldn't be very big at all. Now, of course, and so what that implies is the costs of climate change are not going to be equally spread around the globe. Now, an alternative version of this is, well, India knows this at some level. They might not have this exact graph, but they know what their per capita income is, and they know exactly what their income is going, and they know what the United States income and other rich countries are. And they may want to get really rich, just like other developed countries. And the reason they want to get really rich is because they want to flatten this guy out. They want to get rid of the U, just like we've gotten rid of the U that used to prevail in the United States. And why is that relevant for all of this? It's relevant because I think the notion that we're going to get lots of action from developing countries to participate in climate treaties is unlikely, and this helps underscore why. So let me just go on. So this is just a graph of, so why is it so flat in the United States? It's so flat because people ramp up energy consumption on really hot days. This is energy consumption now on the y-axis. And it's the same daily temperature bins on the x-axis. And so when things get really hot, both for comfort and safety reasons, people start to consume a ton of energy in the United States. And you know, India would like to have air conditioning. So here's a graph for India. Okay, so if you were to do the thought experiment which has some limitations. But if you were to do the thought experiment of, if we take today's United States and today's India and just put them at the end of the century, no further income growth, no nothing. What the data are trying to say is the increase in the United States mortality rate would be very small and statistically indistinguishable from zero, about 2%. In India, it would be unbelievably dramatic. It would be a 56% increase in the annual mortality rate. And what this is trying to tell you here is there would be a big increase in energy consumption in the United States. Okay, so let me just try and summarize. If you do this thought experiment of taking today's United States and moving it out to the end of the century, there would be a statistically insignificant 2% increase in the annual mortality rate by the end of the century. There would be larger increases for some age categories, which isn't surprising. But to put that in perspective, even though it's statistically insignificant, that's like losing 2 years of technical progress in lifespans in the United States. So it's a very small impact. There's a big impact on energy consumption. And then the mortality impacts in India are predicted to be substantially larger in the U.S. and concentrated, which I didn't talk about, in rural areas. And I think that's largely because there's fewer, it's hotter there, there's fewer opportunities for adaptation. And it's also worth emphasizing, I'm just using mortality as a proxy here for the full cost. There's plenty of other areas, say agricultural productivity, that would be impacted. And the punchline is that the costs of climate change are unlikely to be spread evenly across the globe. I want to emphasize that this thought experiment that I'm doing of taking today's U.S. and today's India and putting them at the end of the century is going to lead to an overestimate of the damages, because we're not allowing for all the adaptation and the income growth that will come in the coming 90 years. But I think the most important takeaway from all this is this underscores why it's going to be incredibly difficult to have some kind of, every economist's dream is to have a global trading system, or every environmental economist's dream is to have a global trading system for carbon, where people can buy emissions reduction. We might want to do an emissions reduction, but we can buy it in India, and where India will be, and other developing countries will be undertaking their own emissions reductions together in the same market. All that rests on the idea that there's going to be some shared vision of what an extra ton of carbon emitted in the atmosphere is worth, or the damages. And the punchline, I think, from all this is we're very, very far away from having kind of a global agreement on what the costs of carbon emissions are, and that's largely because there's these different degrees of development across the country, across the globe. So that's it.
Model that at least giving people something to visualize, this helps create a useful dialogue?
Some people have a hard, I think that graph is really powerful of showing the U in India, and I think that stops people in their tracks often. Showing that U in India and that it's completely flat in the United States.
Being the oppressor nation has its privileges.
Sorry?
Being the oppressor nation has its
Yeah.
privileges.
A different way to say it is, it's great to be rich, or I guess the converse of that is it sucks to be poor. But since this is a global problem, it bites because we're all in this together.
So there's some chance that showing the fact that poor nation will suffer more might be a lesser.
Well, actually, there's two views on that. It could motivate action, or it could stiffen the resolve of developing countries that they want to get rich so they can flatten out the. Yeah. Getting rich will protect them from higher temperatures at the end of the century, but it's also going to do a lot of good along the way.
So are the game theorists trying to model what the developing countries will do yet?
I don't think they've made great progress beyond noting that basically our valuations of a ton of carbon emitted into the atmosphere are very different. I mean, you know, the other punchline from all this is that the damages in the United States are not going to be that great. And I found that in other settings as well. And, you know, maybe that helps explain why we're not willing to pile money into solving this problem.
I keep hearing about most of the United States drying up, from just the impact of not having nearly as much water as we do. It seems to me it would be huge.
Yeah, so, you know, I'm
Likely to go down the tubes.
I have some research that suggests that might not be true. And the other thing is, remember, this is like we get a 90-year head start on this. So it's like I'm telling you I'm going to rob your house in 90 years. You have 90 years to figure out a way to stop me. So I think, there'll be migration. There'll definitely be population shifts. But if you get 90 years to have those population shifts, I think there's a good chance that you'll come up with some solution to that. I mean, so I actually think climate change is, the greatest challenge of our generation. I just think the costs are going to be unequally spread around the globe, and in order to really engender action in the United States, you have to be willing to accept the notion that many of the costs aren't going to be in the United States. And I mean, and of course, there's the other scary stuff, which is the catastrophes, which we don't really understand much about. Yeah.
Thank you.
Sure.
Thanks everybody for coming today. I hope everybody has my email and phone and I can send you guys slides, I can send you papers, I can send you video, anything that you saw today. And I can also arrange follow-up interviews if you are so inclined. So thanks so much, and